Okay. Oh, should I start?
I don't see a live stream thing showing. Yes.
Oh, it is live on YouTube. You don't see that?
Okay. No, I don't see it. Okay. So we're delighted to have Benoit from Ohio State University, who is going to start the second lecture of the afternoon. We're talking about lifting in the D1, D5 CFT and the T4 puzzle. Over to you, Ben.
Okay. Oh, thanks for the organizer for giving me this opportunity. Today, I will talk about how to use deformation operator to deform the CFT away from the orbifold point and use this to study the lifting in the D1, D5 CFT and the T4 puzzle. These are based on the works with my advisor, Samir Mathur. Okay. We can add a deformation operator D to the orbifold theory. In the deformation operator D, we have the G and G bar surrounding the twist operator sigma. This twist operator can join two strings into a long string or break a long string into two short strings. During this process, we can introduce interactions for P bar or between P bar. And we can also change the winding sectors. And in the following, we will see how to use these two effects to understand something. We will work near the orbifold CFT point and perturb it away slightly. Try to see if we can understand something in the gravity. Okay. These are the results of this talk. So we will develop some tools from the Gavanaran method to study the lifting. And we will emphasize the supermultipolar structure. We will apply these techniques to the simplest case when n1 times n5 equals to 2 and understand the properties of unlifted states, because the unlifted states is PPS is very important in the geometry. And we will also give some insights to find unlifted CFT states due to superstrata. Because the twist can also change the winding sector, so we will try to use that property to resolve the T4 puzzle. Okay.
Are you going to say what the T4 puzzle is?
Yes, I will explain that later. Okay, let me briefly introduce the D1, D5 CFT and the twist operator. So in our notation, we will use alpha to label the doublet for the left moving SU2 and alpha bar for the right moving SU2, A and A dot for the two SU2 from the T4. We will consider the compactification as T4. To build all the state, we can start with this particular state is a product of many component string labeled by I, and the length for this ith string is Ki. The total length is n1 times n5. It carries the left-right moving charge minus half. To find all the ground states, we can act with the fermionic zero mode, D0. The A can be plus or minus for each copy. And to find all the high-level states, we can further act with the positive mode for each copy. You should notice that these are the modes for individual component streams. So they are the modes for copy I. Now let me define the global modes. Global mode is defined as the sum over all of the modes of the over all copies. For example, if you look at two singly one streams, the D0 mode is the sum, the global D0 mode is the sum of D0 mode for copy 1 and D0 mode for copy 2. This global, if you want to, these global modes are the actual symmetry. Oh, the reason we use global modes because they are the actual symmetry of the system. This system has the left and right moving contracted large n equals to 4 superconformal symmetry, and these are generated by the LG, J, and alpha D modes. If you use the LG, J only, this is called small superconformal symmetry. Oh, these are all the global modes. So we if you want to keep the symmetry, we should use only the global modes. Now let's look at deformation. We can deform the theory by adding the deformation D, which has this particular structure. Because this structure, it keeps all the left and right moving this symmetry. And the twist can break string or join two streams. Okay, any questions here?
I think we're good.
Okay. Now let me introduce the Feynman rules to compute the twist operator. If you are interested, you can read these papers. So the problem is we start with the state in the 1-1 sector, in the untwisted sector. And we have a particular state in this sector. So O are some operators in this 1-1 sector. And we apply twist operator sigma at W0. And the goal is to find the state after the sigma in the twisted sector. To find this state, we can start with this operator O and first make contraction, like the usual weak contraction. Replace pairs of O by a complex number C. And after that, whatever operator leave after contraction, you can replace this operator in the 1-1 sector. For example, this is an alpha mode for copy 1 by a mode in the twisted sector. So this tells us how to propagate from the untwisted sector to the twisted sector. After these two steps, we can now let's apply the obtained operators from the first two steps to the state chi. This state is an excited state above the Riemann ground state. So we can see the O here is the Riemann, O2 minus is the Riemann ground state, and we have many alpha pair and the D pairs above this Riemann ground state. So this is the pair creation. By following these three steps, we can get the state in the twisted sector if we apply the sigma to some untwisted sector states. Okay. Now let me introduce the lifting at the second order in lambda. And we will measure the dimensions from the Riemann ground states. So level n states means the dimension h and h bar is n, 0. If we deform this theory away from the orbifold point, we will expect some change of the dimension because the difference between the h and h bar is an integer. So we expect they change by the same amount, small amount epsilon. And because the right moving supersymmetry, the epsilon must be larger or equal to 0. So this epsilon must start at lambda square. If it start at lambda order 1, then you can flip the sign of the lambda and make the epsilon negative. So from here we can know the lifting for this particular the state should start at second order. This is a B, D1, D5, B state. The conventional method to compute the lifting is use the pathological formulation. So we can look at this amplitude x. We put O, the initial state at minus t divided by 2, and put another final state O at t divided by 2, and fill the region between them by 2 insertion of deformation operator, because we are looking at second order effect. If you can compute this amplitude as a function of t, then you can look at the large t limit. And from this large t limit, you can find the so-called lifting matrix. The eigenvalues of this matrix are the lift, and the eigenstates are the zero order states. From here, you can see we look at the terms linear in t from the x. That means the contribution to the x, most of the contribution comes from the region where these two d are bound together, they move together, and so you have a integral over t. So you can see all levels between these 2D, all intermediate state between these 2D at higher levels contribute. So it is a 4-point function. We cannot easily break it this 2 to 3-point function. Okay, it seems we can use this method to compute the lift. However, there are some shortages for this method. The first is, if this O state are in the twisted sector, then the covering space is a torus. So usually it's difficult to find this amplitude explicitly. The second thing is the supermultiplet structure is not clear. You can compute all the O and find some O have the same lift, and you may conjecture they are part of the long supermultiplet. But the supermultiplet structure is not clear if you do not compute this explicitly. So we want to make this clear and show how to use this to simplify the computation. Okay. In 2002, Gava and Naran proposed the idea to break this 4-point function into 3-point function. In the following, we will use an improved version of this method. We will emphasize the supermultiplet structure and make connection to the second-order perturbation theory in the Hamiltonian formalism. First, let's define the projection operator P. It projects states into level N0. So we look at the subspace N0, and the projection is projected to that space only. And we define the operator GP with projection operator in this form. We have projections here. Then the lifting matrix can be written in the following form. It is a purely algebraic form, not it's different than this case. Here we look at amplitude. We have to compute amplitude and take a large delimit. But here is only algebraic form. Okay, because the projection operator P here, you can see if you apply the GP to the state O, the state you will get the intermediate state between these two GP only at level N0. So because of this, we can put intermediate state between them and break this this thing into a product of 3-point functions. And this will simplify the computation. Now all this 3-point function can be computed by using the Feynman rules we introduced of the twist operator. Okay, any questions here?
This projection doesn't throw stuff out that you really should be keeping. It's all kosher.
Can you see again?
Well, I'm just wondering about the intermediate channel. Does this projection remove things from the calculation that really should be part of it? I guess probably not.
Oh, I see. Because we are not put this projection by hand. Because this particular property of large T, we can derive this projection. We are not put this by hand.
I see.
So it keeps everything we need.
Okay.
Oh, another thing, I see. Here, because we use a deformation operator, so all levels contribute between them. But now we use a different operator, G. This is slightly than the deformation operator. So if you put into this form, only the N0 level contribute.
That's what I was really asking is, the previous one has every intermediate channel communicating, but this one you've thrown a projector in which seems to project only on the sort of on-shell channels. I may be misunderstanding something elementary. But...
Oh, because we use different operator. So it's possible if you use the D, you have all the levels, but if you use another operator, you only have the same level states.
I guess maybe I could just add here that what Binshah mentioned is the whole point of the Gamma-Narayan trick, and a trick which has also been used by Geberdier et al. Also in many places, is that if you're applying this to states which are BPS at leading order, then you can actually prove that this is what you get. If you're applying it to other states, it doesn't have to work.
I see. Okay.
But why are things being saturated by only one intermediate state? or maybe I'm misunderstanding.
Oh, you mean this Carbonara method?
Yeah,
I see.
it's a 4-point function. Naively, you would expect it to factorize on a whole bunch of intermediate states.
Yes.
Yeah, that's the question I was really asking, but I think Samir said something that was...
Yes, I was just saying that that's actually how it works out. The fact of factorizing onto this states which he's mentioning is equal to saying that when you do the integral over the plane, if you were working on the plane, you integrate all the way up to a disk of size epsilon around the insertions. And if you have something which is cut off at size epsilon, any higher dimensional operator doesn't propagate out. This is just the Gauss-Narayan method actually put in something which you do on the plane, where you only try to extract the coefficient of the leading log to get the dimension. That thing moved onto the cylinder, which will be more useful to bin for the later calculations, actually looks exactly like this. Because when you want to extract the leading log, there's a lot of terms which just drop out, right? So the anomalous dimension is actually given by this. It's not the full amplitude. You want the part which contributes to the anomalous dimension.
Got it.
Okay, I'll take that as well. Okay, please go ahead. That's good.
Okay. If we use that formula and give the indices some particular values, we can get the value of the lift. And if the O is eigenstate, then we can write this as a mole square of this particular state. And from this formula, you can also see if we apply the same G bar twice, you will get 0. And we can also show the G bar P commute with the lifting matrix E2. So if you start with the bottom member, you can only apply the same G once, and all these 4 members have the same lift. So that tells us the 4 short multiplates join into a long multiplate by the operator GP. So this can simplify the computation, since if we find one of the lifted short multiplates, we can generate the others by applying the GP. And some of you may have the question, it looks possible, it looks nature if you, in the pathological formulation, you only need the 0 order state. But now we transform this into a, looks like Hamiltonian perturbation theory. It seems there's a question, we also need order 1 correction to the wave function, not the 0 order wave function only. So this can be explained by the following formula. So actually, GP acting on the 0 order state is a combination of first order G, 0 order wave function, and 0 order G and the first order wave function. So the first order correction of the state is encoded in the GP also. Okay. Now let's apply this formula to the simplest case, n1 times ny equals to 2. Even for this simplest case, there are 2 sectors for this simplest case. One sector, the sector of 2 singly one strings, and 2 sector, a doubly one string. Even for this simplest case at level 1, we have more than 2,000 states. So if you try to compute the lifting matrix directly, you will get matrix about 2,000 by 2,000. So it's impossible to compute. So we have to use symmetry and compute for the primaries only. To find the primaries, we have to first figure out the symmetries kept by the symmetries keep the long multiple structure, because the long multiple structure is generated by the GP operator. So we have to find the symmetry commute, the modes commute with the GP. So for the left mover, it is the contracted large n equals to 4 superconformal algebra, and for the right mover, it is the D0, the global D0. We can use this symmetries to generate the character for each primary. Then we can do character decomposition. We will compare the character to the partition function. In this way, we can find the number of primaries. So we have the following table. Here, the H labeled level And the A, B, C columns are in the 1, 1 sector, and the D columns are in the 2 sector. Okay. And this J here is the left moving SU2 charge, and the J bar 3 here is the right moving SU2 charge of the third component of right moving SU2 charge. We can fit that long multiplet structure into this table. We will find the bottom member 5 in this long multiplet structure lives in the column A. And the middle member 5 plus 5 minus live in the column D. And the top member 5 plus minus live in the column C. And we can do this in the following. We can use the similar idea as index. If the bottom member has the right moving SU2 charge J bar 3, so the middle member increase the charge by half and top member increase by 1. So you can fit this charge into this table. So the bottom member have -1, the middle member have -half, and the top member have 0. It seems from index the 5 plus and 5 minus can come from column B or column D, but because there's a twist operator in the GP, so it will change the twist sector. So 5 plus and 5 minus must live in the column D. This is also the idea used by index. The first index for D1, D5P with T4 compactification is studied in this paper. However, they didn't use the global mode carefully. So here we use the index. The counting we use is a refined version of this index. And now let me give you an example of this long multiplet structure. For example, at level 1, you have 3 in column A. So you need 6 in column D, 3, 4, 5 plus and 3, 4, 5 minus to complete that long multiplet, and 3 in the column C. So it seems it is possible to join all the states all the primaries at level 1 into 3 long multiplets. And for level 2, we have only 1 in column A, so we need 2 in column D. So in column D, there are 26 unlifted. 2 can be lifted. Okay. So as you can see, we have enough state in column D, so all states in the column A are allowed to be lifted by index. Okay, any questions here?
Can I ask something? So what did you mean by okay? Maltosina-Moore and Strominger has some modified index, and what do you mean by improving their index?
Oh, they will simply count the state at this level, not primary at this level. So sometimes if the state is kept unlifted by the symmetry, but if you use the index, you will, if you just match the charge as U2 charge, you will think they may be lifted, but they are actually kept unlifted by the global modes. So we only look at the primary, but they look at all the state at this level.
So I'm not sure I understand either.
No.
Maybe I can give.
You're saying that they are coarser than what you're doing. You're looking at some more structure inside a multiplet, or I just didn't get it. Oh,
because some states are unlifted because of the symmetry, the symmetry of the global modes. But they don't consider that, and they only match the SU2R charge. For example, if one of the state is protected by the symmetry, but you can find the match of charge for this state, and you will think this state is lifted, but actually it is not lifted by the symmetry.
Is this something that can be captured by some kind of more refined index than
Yeah,
theirs.
yes, I think so.
What is it?
I'm not sure if anyone has done that, but there should be a refined index. But it may not be easy to find the closed form for this index. But you can count explicitly like this and get the unlifted state.
Okay, I will ask you again later. Thanks.
I think there's a paper from Benjamin. They count the state like this by looking at the primary only.
Primary only.
So maybe I could just jump in with a comment. I think what Bin managed to do here was, normally if you want to count with Maldacena, Moore, Strominger, all the protected states at a given level, some of them are new primaries at that level, and some are just descendants of states which were primaries at lower levels. So if something was unlifted at a lower level and you have a descendant, it will obviously also be unlifted. So it's not very useful to count those guys. So it would be great to actually count the guys which are new primaries at that level, which are unlifted. So how do you actually count only the new primaries at each level and throw out the descendants from the Maldacena, Moore, Strominger index? So there was some nice work of Nathan Benjamin, and there was another author there whose name I don't remember. And then Bin also managed to do something similar and actually made this count of actual new primaries and not throughout the descendants.
And that cannot be just explained. I mean, you just cannot count that by some twisted index. You just have to look into the structure of the multiplets.
So Bin had some way of doing it. I didn't completely understand what he did, but he has a computer program which throws out all the descendants systematically. So level by level, he could keep hitting the button on Mathematica and getting these numbers. But I don't think he has a closed algebraic form. I think that's
okay. Okay, thank you.
Probably let Bin continue.
Okay, because there are enough states in column D, so all the state in all the new primaries in column A are allowed to be lifted by index. Okay. So we check explicitly up to level 4. All the state in the column A are lifted. So we first construct all the primaries in column A up to level 4, all these primaries, and we compute the lift, and then find the corresponding members in column D and column C. So we believe it is correct for most of the states in column A at higher levels because there are enough states in column D. And because the twist operator is complicated enough, so if you apply to the state A and you have enough phase space in D, you will generally get non-zero state and lift. Another important thing to notice is at any level in column B, the state is unlifted at second order. It is correct for any level. To explain that, let us write down the right movers explicitly. For the column A and C, we can see the right movers are symmetric between copy 1 and copy 2. For example, for the column C, if you change the copy 1 and 2, you will get minus sign for this factor, minus sign for the second factor. So overall, you get plus sign. So A and C are symmetric, but the column B state here are anti-symmetric between copy 1 and copy 2. If you change 1, 2, you get minus sign. So the result for the unlifted state in the 1-1 sector, in the untreated sector, is simply the descendants of the Riemann ground states, or the state having anti-symmetric left and right mover. So we can think of the first kind of state is protected by the symmetry, and the second one is protected by the something called copy symmetry. The overall state is symmetric, but the left and right mover are separately anti-symmetric. Okay, here I will explain the copy symmetry. So in the Feynman-Lewis of the twist operator, if you move the twist operator, the position of this twist operator around the circle, you will change the label copy 1 and copy 2. However, to compute the lift, we will use the GP operator contains a projection operator P that eliminate all the W dependence. That means the GP only have non-trivial effects on symmetric states, and it will annihilate all antisymmetric states. So this explains why the antisymmetric states in the untwisted sector are unlifted. Okay. Oh, any questions so far? Okay, now let's look at the.
Sorry, can I ask? So maybe 2 slides back, you said that all states that can lift by the index, they lift. But what index were you referring to? This one.
Oh, we refer
All
to the
states
state
that are
in,
allowed to be, yeah, the first 2 red lines in red. Okay.
Oh.
States that are allowed to be lifted by index are indeed lifted. Which index? Is it your index or Madison and Moore Streminger's index?
Oh, so it's the refined index.
The refined one. So the okay, your classification. Okay, thank you.
Oh. Okay, now let's look at the CFD states that propose due to superstrata. So this is a state proposed superstratum CFD states. It has vacuum part and the supergraviton part. The rigid generators act separately on each supergraviton. So in general, the psi are not the eigenstate of the lifting matrix, but we can look at the average because the eigenvalues are non-negative. So in the formula of the lifting matrix, we can see the GP can break a stream or join 2 streams. So the GP can join 2 vacuum, so we can introduce an interaction between vacuum and vacuum, interaction between vacuum and a supergraviton, interaction to break a supergraviton, or interaction between 2 supergravitons. So we find only the last interaction caused the lift. So that's the interaction between a supergraviton and another supergraviton. It is unreasonable because if you just put 1 supergraviton in the ADS, you will have the first 3 kind of interactions. Okay. So we check explicitly for the following 2 kind of CFD states. The first one, the base space is the 0, 0, and the second one is plus minus. And we show they are all lifted. Now let's take a large N limit because the twist operator can join any 2 supergraviton. So the lifting matrix E2 is proportional to the N square. And by matching the string spectrum in the PB wave limit, we can define the 't Hooft coupling G, and G much less than 1 is in the perturbative CFD region, and G between 1 and the square root of N is in the gravity region. So the E2, we can write E2 in this form. So G is a fixed number. It can be small or large, but we can see it's proportional to N. So it is non-BPS at large N. So it looks like if the geometries are exact BPS, maybe we need some modifications to the proposed CFD states, this kind of CFD states.
How did you go from, so the first, on the top of the slide, you've got, it goes as N squared. And now how did it become order N? Oh, you swallowed something. Oh, I'm sorry, I'm being stupid. Yeah, you just swallowed up N to the half in your coupling. Good.
Oh, yes.
I'm happy.
Here we use 't Hooft coupling.
Yeah, thank you.
So the tools we have to make unlifted state is the following. We can use the global modes. It can be rigid, like the superstrata, or non-rigid, the higher modes. We can also mix with longer component streams, and we can use antisymmetric right movers for if the right movers are fermionic. For example, if we look at this particular CFD states, we can write down the product of this 0, 0, and we sum over all possible permutations of the right movers and give them proper sign. We can, in this way, we can symmetrize the right mover, and if we do this replacement, the state will be unlifted at second order. A very important thing is to check all this, because we have more than one tools to make unlifted state. It seems it should not come from only one of the thing. It may be very complicated. So the next thing we should do is to find the unlifted states that pass the one-point function check, because that's a quite non-trivial check and can tell us how to assign the P charge to the D1, D5 to make D1, D5 P state. Oh, any questions here? Okay, now let me tell you the story about the T4 puzzle. The Riemann ground states of the singly one string can be written as the following way. So the left and right mover can be plus minus 0, 0 tilde. Okay, the 0, 0 tilde has one D0 mode and plus has two D0 modes. Now let's consider a state with n singly one streams. We consider the following two classes, the X4 states and T4 states. For the X4 states, these are states consist of strings with plus and minus, because they are oscillated around non-compact direction, so the geometry have short throat. The traveling time can match on both sides. And this R is the size of the Y circle, the CFTs. So the traveling time for the CFT is R, because they are all singly one streams. However, for T4 state, we use the string 0 and 0 tilde. The oscillation is around the compact direction, T4 direction, so the geometry is believed to have long throat. So we cannot match the traveling time. The traveling time in the gravity is much larger than the traveling time in the CFT. So this is the so-called T4 puzzle. To get the traveling time in the geometry, we have to send a probe in the radial direction. In the CFT, it is to add PP bar excitations. So we will explain in the following. When we add low energy PP bar excitation, the deformation operator can join strings in the T4 states, but not strings for X4 states. Suppose we start with the following initial state. This is a state with n singly one strings labeled by copy n1 to n. And we put PP bar excitation on the copy 1. And at step 1, the copy 1 can join another singly one string, for example, copy 2 into a string with winding 2. And next step, we can get a string with winding 3. So at step K, the string will become K plus 1. Usually this joining process is very difficult to keep track of, and it's hard to get any physical result from this computation. However, things can be simplified in the following limit. If you look at the large K limit and keep the PP bar excitation at order 1, so we keep the fixed PP bar excitation. So the reason we can the computation can be controlled in this limit is, for example, if we look at step K, the winding K string become K plus 1. We look at the mode in the string of winding K, the alpha mode. It will become an alpha mode in the string K plus 1 by the propagation rule. And we will see if we change the mode number from P to another Q, where P is not same as Q, then we get 1 over K suppression. If we keep the mode number P, then we have no suppression. So the mode number tend to stay the same in the joining process when in this large K limit. Okay, is there any questions?
This seems to violate energy conservation, though, because you've got a slightly different energy state. So did something happen?
Oh yes, because we have so many modes. So the some modes get higher energy, some modes get lower energy, but the overall energy should be conserved. Okay. Oh, is that clear?
Yeah, please go ahead. Yeah, go ahead.
Okay. So we can also consider use the constraint from symmetry. If you join k strings into a strings with winding k, the total charge cannot be larger than square root of k, because the charges are carried by the fermionic mode, and if you have too much charge, you need to have too many Ds, and this, because they are fermionic, you will carry the energy you carried will be larger than the initial energy. So we only consider the almost charge neutral states. So for X4 states, it can be the state with alternating plus minus streams, or plus plus minus minus, all this kind of combination. And we should also consider all the T4 states. Now let me estimate for the T4 state first. At step K, we will join a winding K into a K+1 string. During this process, we absorb the following left mover. This is a 0 or 0 to the left mover. And the amplitude for this left mover in the large K limit can be computed. So the left amplitude is 1 over square root of K. So if you combine the left and right mover, is 1 over K. This is comparable to the energy level of that system is 1 over K, so it's almost a discrete system. So you can estimate the time from K string to K+1 string, and the time is K. If you compare the time of moving around the strings with length K, which is K, you can see the time for the joining is comparable to the time of complete a string. So that means before the PP bar meet and leave the fuzz ball, there's enough time for the joining into longer streams, because these two energy scales are comparable. Now we can look at the X4 state. At step K, we will absorb a plus string, a plus left mover. The amplitude is 1 over K. It is smaller than the previous 1 over square root of K in the large K limit. If we follow this by absorbing another minus, we will get 1 over K also. That means the amplitude is 1 over square root of K. So the time for the joining is K squared. So you can see the time for the joining is much larger than the time to complete the circle, which is K. So that means before the PP bar meet and leave the fuzz ball, there's no enough time for joining into longer streams. Okay, here's a summary of our results. So, okay, thank you.
Can you put the summary back up again, just so we can stare at it while questions coming in? Anything else you want to add in summary?
Okay.
You got a couple of minutes.
Or maybe I can just emphasize, or maybe I can just read this. So we find the GP bar are the operator that join 4 short multipolate into a long multipolate. And we consider the simplest case n1 and phi equals to 2, and we find in the untwisted sector, all the unlifted states are either protected by the symmetry, these are the global descendant of the Riemann ground state, or protected by the copy symmetry, these are the states with antisymmetric left and right movers. And we also apply this formula to the proposed CFT duo of superstrata, and we find they are all lifted at order n, at large n limit. So that means we need modification at order 1, because we only need 0 order state to compute the lift if these states are lifted. So we need correction for the 0 order wave function, not first order wave function. We are not looking at small correction to the state. So, and the last point is to resolve T4 puzzle, we have to add the low energy PP bar excitation and consider the deformation. And it can tell us the difference between the T4 and X4. Okay, that's all. Thank you.
Thank you. Questions, guys? comments?
Hi. Can I ask a question?
Oh, please, absolutely.
Oh,
Yeah. So just to understand, so when you look at the three-charge case, so states with non-trivial momentum charge as well, do you find states that are unlifted, so they are protected, but they have both left and right angular momentum? From what you say, this is the case because it's sufficient that the right moving wave function is antisymmetric, and then the state is protected. So you can have states that have J and J tilde different from 0.
You mean the unlifted state for PP bar?
Not momentum. I'm talking about the J3 charge.
Okay.
Angular momentum, right?
Oh,
so things that have left and right angular momentum.
Oh, you mean apply the J here?
Yeah, or apply the J, for instance, or have strands that carry angular momentum both on the left and the right, and they are. I mean, you see, because I think a lot of people have in the back of their mind that since there is no extremal black hole with angular momentum both in the left and the right, then there are no states that have that are protected and have angular momentum both on the left and the right. So I just want to fact that you did find counterexample to that case, to that statement.
Okay, I see. If you add the left and right, the PP bar by using the global mode, for example.
Yeah.
Use the spectrum flow for both the left and the right, then you can find the unlifted state. This is protected by the global modes, the first kind of thing. It is a fractional spectrum flow, but if you rescale the stream, it is actually the non-rigid generator, the symmetry of the non-rigid generator of the symmetry. So it is protected.
Yeah. Okay. Maybe we can discuss further offline.
Okay.
Okay. And any other questions?
I had a question about the T4. Sorry, there's somebody else?
No. Go ahead, Joseph, please.
I had a question about the T4 puzzle. So what you are saying is that the 0,0 strands, which are basically modes on the T4, they actually join into plus strands, and the plus strands just become longer, and because of this momentum mode going through them, right?
All the 0,0 join another 0,0 become longer and longer.
Yes. But the point is, at some point, this process has to stop, right? Because at some point, you'll have, let's suppose you have half plus strands and half 0,0 strands. Then, essentially this state, the plus strands are going to become double size, or the 0,0 strands become much longer, but.
Yes. So if you have order n plus strand, then you cannot join this plus because we don't have, because the constraint flow symmetry, we don't have enough energy to further join the plus.
But do you need, but for the 0,0s to join the plus, you have no energy.
Oh,
you need no energy.
Only to join the 0,0. Then you have both short string and long strings. Then the third may be short because if you move in the short string, you will get very small traveling time.
So at some point a few years ago, we had this string fattening hypothesis, according to which both for the superstrata and also for two-charge states with 0,0 strands, the way to explain the mass gap is to actually get the 0,0 strands to join the plus strands. And if you have, for example, a superstratum which has 15 plus strands, they all become very, very fat. They get a length which is n1 and 5 over 15, and this explains perfectly the supergravity mass gap in the bulk. This is for superstrata. Now the problem is we tried the same game for two-charge supertubes. Those are some unpublished notes which Andrea Galliani and Alessandro Bombini have with me, and we tried to compute the same fattening idea. Again, you have let's say you have a bunch of plus strands and you have many 0,0 strands, and the question is, do you fatten the plus strands into being as long as you can, and how do you compare the mass gap, what you find by doing that, to the mass gap you find in supergravity? And the point is, for the two-charge systems, somehow the things don't match. So in the 3-charge system, your story makes perfect sense. Again, if you just assume the 0 zeros to dissolve when you move away from the supergravity point into plus pluses, the plus pluses become, you know, very large. They're more or less equal size for some reason, probably based on statistics. And then this gives you exactly on the nose the supergravity mass gap. You know, this works, again, you take a superstratum with 17 plus strands, lots of 0 zeros, they just merge and the mass gap is 17 over n 5 times 2, which is exactly what you expect from the CFT if you have these fattened states. But in the 2-charge system, for some reason, it doesn't work.
Oh, here we only show it can become longer and longer, but we don't know where it stops.
How long?
Yeah, so we cannot. Oh, when the K is much larger than the PP bar excitation. So
Joseph, I think he has to make a PP bar excitation in order to do this. So did you make, when you did this in the 2-charge system, did you have a PP bar
You solve the wave equation. The PP bar, solving the wave equation for the, you solve the wave equation in the Bannon and you compute the mass gap.
No, but you said a 2-charge system. What Bin's looking at, I think, is intrinsically a 3-charge system. Because
No, he's putting a perturbation on top of a 2-charge system. He doesn't have a 3-charge. His background is 2-charge. He has a 2-charge supertube, which has plus and 0, 0. And he's putting a perturbation. The perturbation is a non-supersymmetric mode. And he's breaking it into right movers and left movers, which then start going through the CFT. And, you know, they start, you know, plowing through these modes and, you know, merging them and joining them. It's a very beautiful process which you have, actually. It's a very beautiful process. I mean, you have the mode going through the CFT and, you know, essentially it's merging and joining all these things together.
But okay, the thing I'm trying to separate out is if you want to join 0, 0 strands, there's no energy cost.
Yeah,
whereas if you want to join plus pluses, you've got an energy cost, and that's got to be, the bill's got to be paid by somebody, and Bin's paying that bill with his momentum.
He's not paying the bill, actually. He's just joining 0 zeros. He's not joining plus pluses.
Okay, we better figure out what she's doing.
Yeah, so I actually wanted to ask about that. So Ben, what was the role of adding the momentum excitations? Why did you need to do that?
Oh, if you don't have the PP bar excitation, then the twist operator, because you cannot change the twist sector by the deformation operator.
Right.
Why?
So you have to add the PP bar to change the twist sector.
I think if you look at the bottom of the slide, Emil, if you don't, when you join 2 twisted strands, which are plus plus, you've got to have a fermion excitation or some kind of excitation on them as a result, and you've got to pay the energy budget from that. And if you don't have some ambient energy there involving these alphas, you can't do it. Isn't that?
But the 0, 0 strands can just rearrange among themselves.
Absolutely.
So why?
Oh, because
why do we
if
need
you
to momentum to do this?
Oh, because if you start with 0, 0 strand and apply the twist operator, apply the deformation operator, because deformation has the supercharge, so it won't do anything for this. It will not join 2 strings into a longer one.
Really?
Could I just say that in a different way?
Yes.
There is a whole set of BPS states, right? Take the 0, 0 ones. There's a whole family of them, right? Now, you can say any one of them, you add a deformation, you can say it becomes another. Suppose there are 10 of these states. But even after any amount of deformation away from the orbifold point, there's still going to be 10 guys. So the point is, you may say this particular one deforms to a multi-wound one, but the singly wound one is still a state in the same family, because you can make any linear combinations, all linear combinations of these 10 being singly wound, multiply wound, mixed things, they are all actually in the same family. So you can actually, whether you add the deformation or not, even with the deformation, you can say, let me look at the state where they are all singly wound, and that is a BPS state, because the number of states remain the same.
Sure, but when you look at the supergravity solution, if you look at the solution in the supergravity regime that has the same labeling, it has a very large redshift without adding the excitations.
That is the puzzle, right? So the puzzle is that on supergravity side, whatever you do with the torus, you get a deep throat. But the torus modes, the vibration modes in the torus can correspond to singly wound, doubly wound, very highly wound. Okay, right. But the throat is deep in every case in gravity. On the CFT side, you still have the same number of family of states. You can say, I prefer this linear combination after turning on the coupling, or that linear combination after turning on the coupling. But the fact remains that all linear combinations are degenerate. Any particular combination, including the one which is all singly wound, is still an exactly BPS state. So you could take that one and say, what do I do with this guy? The throat is still deep on the gravity side, but there's an exact state on the CFT side still, where everything looks singly wound. And then what Ben is saying is, well, to see what the singly wound means, you're going to throw something in it. If we throw something, what the singly wound strings are doing is that they actually start joining up. So at the BPS point, all the singly wound and the multiply wound were all equally good states because they are still 10 BPS states. But when you throw something, the energy of what you throw in start joining the things to make the string longer as the evolution proceeds. So you can see the physics of the deep throat emerging. But this you can't see if you don't have the twist operator.
But doesn't the twist operator also break them up? Or are you telling me that once things sort of scramble into more fractionated modes, they won't then break again? They're protected against breaking.
They can break again. So there are some combinatorics, right? Because when you start, there are a large number of singly wound, and breaking something means
but then why what I'm trying to understand is, why does chucking in a momentum wave bias it in favor of joining up to make very long strands, as opposed to just, there was an equilibrium where you could sort of say, okay, I've got long strands or short strands, and the twist operator, the deformation operator, breaks or joins them.
That's absolutely right, but that will happen much later, because suppose you start with 1,000 singly wound. Now, if you want to twist one guy with somebody else, right now the only other guys available are singles. So you join two singles, you get a double. Now there is some chance the double breaks back to two singles, but that's very small because the twisting has to then couple strand 1 to strand 2. So there's only one possibility. But any of these two with any one of the other n-1, right, will make it triple. So at least until the whole thing becomes as long as, like, some
root n1 and 5.
Yeah, something like a big depth. You're not going to actually get breaking as a very dominant fact.
Okay. But why does this require the momentum, or doesn't it?
So it requires the momentum because before the momentum, you can still try to find the eigenstates. So we do that, right? The perturbation theory, you were showing you can find the eigenstates. But because the family remains with the same degeneracy, there were 10 states before perturbation, there are 10 after perturbation. Even after perturbation, you can take the member where all of them are singly wound and say, hey, I have a puzzle. So if you don't throw anything on it, they can all singly wound is still a state in the supersymmetric sector.
But why does that picture change when you throw in a momentum state? Why does it suddenly decide everybody's going to join up?
Because now with the energy that you have, what's going to happen is not only that they join, the guy you threw in, the alpha-1, as Ben was showing, it becomes 2 copies of alpha-1/2. And then it joins to 3, it becomes 3 copies of alpha-1/3. So he actually computes what evolution will happen when you throw some energy in. And the evolution is actually taking you in that direction. So it's a dynamic which you observe from the actual interaction.
So this is a free energy argument, isn't it? It's simply saying that essentially, if you've got 1 unit of energy, it will prefer to go into many, many fractionated modes.
So it's not exactly free energy. It's actually more like dynamics. That when you throw it in, you just actually compute the evolution of the wave functional. And the wave functional, if you start with all singly wound, under this extra energy you dump in, which way does it evolve? So it's not actually combinatorics until you get fairly deep down, and then you can use combinatorics to get an approximate idea. But in the beginning, it's actually dynamics, that alpha-1 breaks into alpha-halves if the strings are 0, 0, but not if they are plus, because then you have to pay the energy budget for the fermions. That's just dynamics. So he computes the actual amplitude for this transition using the deformation operator and checks that this breakup will happen before the 2 parts have had time to go around. Because if they've gone around the singly wound string before this joining with the next string can happen, then you still have the puzzle. They'll spit out before they can actually make use of the longest string. So you actually have to compute the rates. So he actually computes the rate and sees, does it compare? How does it compare with actually going around? And then he was showing you it joins before it can go around.
Emil, did you want to follow up? I should.
Nope.
Okay.
Or maybe I can add something here. If you don't have any PP bar here, and you start with the singly wound string, and the deformation will not change the sector. If you want join 2 string, you have to pay some energy. You will get excited state, not the ground state. So the deformation will not change the state without any PP bar excitation. So we have to add pp bar to make the state change to large winding sector.
Even if it's 0, 0?
Yes, even for 0, 0, it looks like you can make longer 0, 0, but that's impossible because the supersymmetric structure of the deformation.
Any other questions or comments or?
I have one, but I'm happy to ask it in the informal.
Well, just ask it anyway, and I can always shut you up in 2 or 3 minutes.
Okay. It's just a general question, so nice talk. I'm wondering about the difference between T4 and K3. So, of course, everything you said here was for T4. And for K3, the usual story is that life is much simpler, that all the chiral primaries are bosonic, and so they can't join up into the short multiplets, can't join up into long multiplets in the way you describe. And so they're short multiplets at all values of the moduli. I just wondered if you had anything to add to that usual story.
Oh, you mean the lifting problem for the K3?
For K3.
Technically, the thing I know is for K3, you can view it as a Z2 orbifold of T4.
Mm-hmm.
So it looks like you introduce further more twist sector, so it looks difficult to compute. Actually, there's a paper doing this. I'm not sure if we can generalize these techniques to a very high level.
Mm-hmm. Right, because it seems like that could be part of the story that relates the two things we've been describing in the last couple of days. That if we think about the superstratum states on K3, then the story about being protected or being short multiplets at arbitrary points in moduli space seems maybe a lot simpler, and that they should be protected. Okay, the 3-point functions are protected, that's clear, but the states should remain in short multiplets, short moduli for K3, and then this physics of lifting seems to be a difference between T4 and K3, if that story all goes through.
Okay, I have to think about this.
Sure. Yeah, we can also follow up in the discussion session later. Nick, I think you're muted.
I was trying to be good. I was just had a question about if I went looking for this lifting in supergravity and I wanted to try and do a dual calculation of this lifting energy, the question would be, what would I do? And I'm not sure I know how to start doing that calculation, but there's a prediction here in some sense from the CFT. I was wondering whether there might be a way to compute the dual of this E is G squared order N. Supergravity.
My perspective is maybe we need to change the CFT state to make it unlifted.
Yeah, but I kind of like to look at lifting as well and just see what happens. You know, so I've got some perturbation that I'm going to do on this thing, and I'm going to try and estimate its energy. It might be an interesting, there's a set of interesting exercises here, I think, for supergravity, which is looking at things where, you, Samir and Sean and you have been looking at these modest liftings of states. And the question is, can we find holographic duals of these?
But sorry, Nick, you already start very far from the orbifold point in supergravity. So how would you do the perturbation around?
It's a good question. It's an idea I'm just trying to throw out there. I'm just trying to say, okay, suppose I turned on some background field that's an excitation of the torus. Could I get an energy estimate of what that would do? Maybe it's bullshit. I think perhaps we should reserve that for discussion later, though. And bring the section to the end. We'll resume again in 25 minutes with Emil.
Let's thank the speaker again.
Thank you indeed, Ben. That was great.
Oh, thank you.